Our today's discussion is on simulation of double-stage single-phase grid-connected solar photovoltaic inverter using MATLAB. This is the basic structure of a double-stage single-phase solar photovoltaic inverter. In a double-stage system, the solar PV is first connected to a boost converter. The output of boost converter is then connected to the inverter, followed by an LCL filter, which is connected to the grid. Now I will give the specification of the complete system. Open circuit voltage of PV array is 309.5. Operating voltage range is in between 250 to 300. Value of boost inductor is 20 mH. Switching frequency of boost converter is 5 kHz. Value of DC bus capacitor is 3000 microfarad. Inverter switching frequency is 10 kHz. Value of filter inductor is 4.06 mH, 4.35 mH, and filter capacitor is 6.23 microfarad. Grid voltage is 230 volt RMS at 50 Hz. Rated power of the system is 2 kW. This is the complete controller block diagram of a double-stage single-phase grid-connected solar inverter. MPPT controller is implemented in the boost converter. DC bus controller and grid current controller is implemented in the inverter. PR controller is used in the current loop. Now we open the MATLAB and start doing simulation. First add a solar PV array. Set number of series and parallel strings for 2 kW rated power. Select the module type from the list. Now I will show you the VI curve of the selected array. This is the MPP point corresponding to 1000 irradiation level. And this is for 500 irradiation level. And this is for 100 irradiation level. This is the open circuit voltage of the array. And this is the operating voltage range. Now we need to check this box. Add a constant block. Set irradiation 1000. Set temperature 25 degree. Add a series RLC branch. This is the input bus capacitor and set its value 500 microfarad. Set capacitor initial voltage 309, which is same as the open circuit voltage of the array. This is the boost inductor and set its value 20 mH. Add a MOSFET. Add a diode. Add a voltage measurement block. Add a go-to block. Name it as VDC. Now add another MOSFET. Add a from block. Name it as PWM1. Name it as PWM2. Name it as PWM3. Name it as PWM4. This is the DC bus capacitor and set its value 3000 microfarad. Add a current measurement block. Add a go-to block. Name it as IINV. This is the inverter side filter inductor, and set its value 4.06 mH. This is the filter capacitor, and set its value 6.23 microfarad. This is the grid side filter inductor, and set its value 4.35 mH. Name this current as I grid. Add an AC voltage source. Name this voltage as V grid. Now we start building the MPPT blocks. First, add a bus selector. Add PV voltage and current into the bus. Add a unit delay block. Set its sample time 1e rise to -4. This is the MPPT block, which I have been discussing in many of my previous videos. So I used the same block here for the simulation. You can watch the previous videos to understand more about this MPPT block. I have made 3 changes here. Vref max changed to the open circuit voltage of the array. Vref init changed to the MPPT voltage of the array, and delta Vref changed to 0.05. Everything else remains the same. Now add a sum block. Add a PID controller. Set its KP and KI values. Add a relational operator. Add a repeating sequence. Set the switching frequency and amplitude of the carrier signal. I'm using 5 kHz sawtooth wave with amplitude 1. Now we generate alpha-beta voltage waveforms. Add a first-order filter block. Set filter type low pass. Set its time constant, 1 by 2 pi into 50. Add a gain block. Set its value to. Add a go-to block. Name this voltage as alpha. And name the original grid voltage as beta. Now we build the phase locked loop. First add a mux. Set number of input as 3. Add a constant block. Set its value 0. Add an alpha-beta to DQ0 transformation block. Add a sum block. Add a demix. Set number of output as 3. Add a PID controller. Set its Kp and Ki values. Add an integrator. Add a FCN block. Type the expression cos U1. And here type the expression sin U1. Add a go-to block. Name it as cos omega t. Name it as sin omega t. Now we start building the DC bus controller and grid current controller. First add a constant block. Set the reference voltage 400 volt. Add another sum block. Add a PID controller. Set its Kp and Ki values. Add another product block. Add another sum block. Add a gain block. Add an integrator. Set the gain value 8.5. Set this gain value 986.8. Add another product block. Add a goto block. Name it as Vref. This reference voltage is used for PWM generation. Add a relational operator. Add a gain block. Set its value -1. Add a repeating sequence. This is the carrier signal used for PWM generation. I'm using 10 kHz triangular signal as the carrier, with amplitude -1 to 1. Add a logical operator. Connect all PWM signals to the gate terminal of each MOSFET. Now add scope to view the result. Add DC voltage to the scope. Add grid current to the scope. Add grid voltage and current to the scope. Add a power guy block. Open parameter settings. I'm using fixed step solver type with step size 1 microsecond. Set simulation time 3.5 seconds. Add a product block. Add a display block. Here we can see the output power generated by the PV array. I forgot to change the parameters of the AC voltage source. Set its peak amplitude 325 volt and frequency 50 Hz. Now run the simulation. Here you can see how the power is climbing to the MPP point. Now it has reached 2000 watts, which is the MPP level for 1000 irradiation. Now we will try to change the irradiation and see how the power output changes. When I made irradiation 500, power becomes half of the previous value. Similarly, you can try different irradiation levels. So whenever we change the irradiation, power is changing to the corresponding MPP value. Now I will show you the voltage and current waveforms. Run the simulation again. This is the DC bus voltage, which is regulating at 400 volt. This is the grid current. This is the grid voltage and current together. Both waveforms are aligned in phase, which means we are sending active power to the grid. Now I will try to change the irradiation level gradually. For that, I need a repeating sequence interpolated block. Set the output and time values. Initially the irradiation will be 1000. When the time reaches 0.5 second, it starts decreasing. When the time reaches 2 seconds, it starts increasing. And it reaches back at 1000 when time reaches 3.5 seconds. Now we connect this block to the PV array. Run the simulation again. Here you can observe the changes in the grid current with respect to the change in irradiation. Initially the current was constant, then it started decreasing. Once it reached 2 seconds, it started increasing again. This is the grid voltage and current together. And this is the corresponding DC bus voltage. This is the end of this presentation. Thanks for watching.